Okay, good morning, everyone. Welcome to our colloquium for week 3 of the semester. I'm very pleased to introduce Doug Wright from Drexel University in Philadelphia, who will be talking about random FPUT lattices. So Doug obtained his PhD from Boston University under the supervision of Gene Wayne. After a few postdocs, he took his current job at Drexel in 2007, where he works mostly on proving rigorous quantitative descriptions of wave dynamics in infinite dimensional Hamiltonian systems. Before I hand it over, we will be recording this talk. We will open up for questions at the end, at which point, please feel free to unmute yourself. With that, thank you again, Doug, for being here and for accommodating our time zone. It's all yours.
Hey, what's going on? Hold on, I need one more thing to work on my computer before I can get going here. Hopefully this works. Is there a password for the meeting? 268347.
Yeah.
Haha, there I am. So you got 3 of you now, right?
I just see your whiteboard. I don't know what other people see.
Okay.
I see 2 whiteboards and a blacked out Doug Wright.
Yeah, I gotta start the video. Hi Robbie, how are you doing?
Yeah, good. How are you?
All right, I got an annoying. There, can you hear me?
Yeah.
Yes?
Yes, we can hear you.
All right. Look at this. I'm even dressed like Robbie. I'm wearing a t-shirt and baseball hat. So I feel pretty good about that. Everybody, I'm really excited to be here, and I'm sorry about the screw up. I'm sure this isn't the first time this has happened in this weird situation we're in with speakers from America. And if it is the first time, well, then I'm glad to be really special. So I'm going to talk. There's 3 boards here. I teach from my basement because of coronavirus, obviously. And I have this set up where I talk at the board, and sometimes I talk into this one, like when I'm being funny. And then and you can read the board. And this other one down here is going to be where I'm going to show you some simulations. So I got to fire up MATLAB and we'll get going. And I'm really sorry about the delay here. So I'm gonna have to share my screen. Share the screen, And I don't think I have anything embarrassing in background. Okay, so let's go to the board first. So I'm gonna talk about random FPUT lattices. So FPUT stands for Fermi Positive Ulam Singu, and it's a thing that people study, you know, in this business. Can you see me on the board, or should I unshare my screen? Let me unshare my screen. Sorry, I was going to practice this tomorrow, but I didn't. Okay, now you can see me at the board. There we go. Okay, so here's the thing I'm interested in is you have a mass. It's like a weight or something like that. It has a mass m1, and then you have a spring. And in this talk, this spring is just going to be a linear spring. It's going to obey Hooke's law, like the force is exerted, you know, proportional to the how far it's stretched, and that proportionality constant I'm going to call k1. And then I'm going to put another mass here, m2, and you'll notice that I've drawn it so that it's a different size, so it's, I guess, smaller. Okay. And then I'm going to connect another spring to it, K3. And then maybe there's like a really big one here. That'll be M3. And I'm going to keep on doing this forever in both directions. Okay. And this would be, I guess, M0. And there'll be another spring here. This would be K0. And so this is like just a big, long, wiggly object. Okay. So it's sort of a really simple-minded schematic of like maybe like a long molecule, right? Like it's not. I'm not saying that it is this, but like you could imagine that if you're devising a toy model for DNA or something like that, DNA is like 4 different types of molecules arranged in a rather haphazard fashion, coupled with some sort of chemical bonds. It sort of would look like this. I'm not saying that that's what it is. I'm just saying that's where that's sort of a vague motivation of what you're going to study here. Okay. Now, there's not going to be any dissipation in my problem. There's going to be no friction. There's not going to be any anything like that. And the springs are purely linear. Now, the classical FPUT problem, all the masses are the same, all the springs are the same, but they're non-linear. That's not what I'm doing. I'm doing a slightly different thing. The motion here is, despite my sort of pessimistic tack on it, it's going down to the left. The motion here is all purely side to side. This is supposed to be in a line, a horizontal line from -infinity to +infinity. And the particles only move left to right. They don't go up and down or out of the board or anything like that. Okay. If you set yourself up and you do your Newton's laws, what's F equals ma, right? And so that's the ma, xj double dot. So I'm writing down the equation of motion for the jth mass. So that's good. The position of that guy's x1. This is x2, x3, and so on. And what do you get? You get kj xj plus 1 minus xj minus lj. I'll tell you what lj is in a minute. Kj minus 1, xj minus xj minus 1 minus lj minus 1. So this is the equation of motion for the jth particle. Of course, there's infinitely many of them. So we have an infinite dimensional dynamical system, which is really just Newton's law, but there's a lot of them. The k's and the m's, you know what they are. What are the l's? The lj's are the relaxation length of the jth spring. Okay, so each spring possibly has its own length, and so I'll just incorporate that in this way. And if you stare at this this quantity in this parentheses right here, you'll realize that this is the distance the jth spring is stretched relative to its relaxation length. So this is just Hooke's law, okay, a bazillion times. So that is the system I'm interested in. Now, the m's and the k's ultimately are going to be drawn randomly. Okay, they're all going to be positive. I'm going to draw them from a distribution that's, you know, strictly bounded away from 0 and isn't infinite or anything like that. But you could think of flipping a coin for each j between 1 and 2, and for each k between 1 and 2, right? And so to motivate this, and this is a colloquium, so I thought I would, do a lot of videos because that's more fun at colloquia. So that's what we're going to do next. I'm going to show you some simulations of this system, and I'm going to tell you basically the whole story, and then we'll do the math part of it. Because I started late, I might not get all the way to the end. All right. So now I will share the screen again. Share, and then you'll see there's the email, and there is my thingamajig. There's this. Hold on, I'm trying to make this. There we go. Did I share the screen? Can you see it? Can you see my screen? I hope so. Can I get a yes?
Yes, we see your MATLAB.
Yes, perfect. All right, so here is the first one. I gotta move Justin out of the way. Okay, so in this figure here, what I've got is each red circle is one of the circles that was on the blackboard. So that's a mass, okay? In this simulation, they're all the same. They all the same weight, and I couldn't figure out a way to sort of animate the springs, so the springs are in there, but you can't see them. So I'm just showing you the position of each mass, and you'll see that what I've done here is I've bunched them all up near the in the middle there. So more or less they're 1 unit apart when they're far from the origin, but near the origin, or I guess near -3. I'm not sure why that is, but they're sort of all bunched up. So I squeezed a bunch in the middle, and the rest are out to the side. So if I make with the clicky, it's going to run. Okay, so the springs, of course, unfold, and it shoots out this wave of compression. Okay, so that's sort of what happens. I mean, you're probably not so surprised by that, but let's just look at it again to sort of see what's going on. So there's a very characteristic velocity going on here. The wave of compression is sort of localized as it runs, and the one thing you'll notice is that the particles themselves only move for a little while, right? A particle moves and then it kind of comes to rest. This simulation, it cuts off at -20 and +15, but I'm actually simulating on a much bigger domain. About 1,000 of these particles are on there, and I'm just cutting off and showing you what goes on in the origin. If you zoomed out, and I'll do that in a minute, you would see that that wave of compression was going on forever. So this is the homogeneous problem, and it's got this definite wave-like behavior going on. Now, a better way to visualize this is not to show where the individual particles are. That's the top graph right there. The better way to do it is to plot the relative displacements. So the top one is exactly what you saw before, but below that, what I'm plotting here is the distance. So you'll notice that the axes are different. Here I'm plotting x, and here I'm plotting j. So this is the particle index, and what I'm showing here is what I'm calling r is just xj plus 1 minus xj. So if j is 0, that's okay. I got things a little bit. J equals 0 is right about here, I guess. The distance between adjacent particles is pretty close to 0 and is in fact 0. So they're sort of like squished all the way together. Okay. Now these pictures I'm comparing apples to oranges because this axis is x and this is j. But when I make with the clicky, you're going to see sort of what happens. So they're squeezed together here. Notice that this is 1 and this is 0. What happens is the wave of compression spreads out, and you can kind of see that they're comparable, right? There's something like the speed is comparable in the way I've set it up here. Okay, let's just do it one more time just to get the idea. And so the bottom picture is a little maybe more in the way that we typically think about things moving in differential in PD anyway. We have a fixed x-axis, and then the y-axis is some quantity of interest. Okay, and there's still the same idea of some localized object moving with a characteristic speed. All right. Now everything I showed you was for the homogeneous problem, not a random problem. So this next one is the same as the last one, except now I've randomized things. So I've drawn the size of the objects from a random distribution just using the random command in MATLAB, and I've distributed them I've distributed their positions in roughly the same ways as the last one, and I do the same thing, and then I'm going to run it. And now you'll notice kind of the same thing is happening. There's still a characteristic motion, in to out, but there's like some junk left over. This one runs a little bit longer than the last one, but it's not quite as nice as what we saw before. There's still a lot of residual motion going on, and it's not quite as clean. Okay, so but the sort of overall characteristic was similar. Let's do another one. This is the same exact one from the first ones where you had homogeneous masses, except I've zoomed out quite a bit. So it's exactly the same stuff, only now I'm including far more masses into the picture. And you'll notice that the top one, where I'm trying to resolve each individual mass, it just looks like a big red bar now. I'm too zoomed out to distinguish between individual particles. But in the bottom one, you can still see the sort of shape of the compression, right? The ones near the origin are closer together than the ones far away. And if I run this, this is not the most exciting one, but you run it, and I'm going to run it for quite a long time, you really see this sort of wave equation-like behavior. You see that the initial condition splits into a left-moving part and right-moving part. They're more or less the same. They're moving with some characteristic speed, and they're just going to keep on they're going to keep on trucking. Now, here in a second or two, you're going to see something like here on the trailing edge. You can sort of start seeing it now. There's this divot, except it's not a divot, it's an upside down divot. So it's like a little hillock that is trailing the wave. that's sort of slowly forming. That's the homogeneous FPUT lattice is a dispersive equation, and that's a dispersive effect. It takes a long time for the dispersive effects to kick in. But I just wanted to include this to sort of see that there is some dispersive effect going on. Sim5. Sim5 is the same as the one I just showed you, only now it's the randomized one. So you're not going to see that dispersive effect because it's going to be occluded by the random joscillations that are joscillations. Is that a word? It's going to be, it's going to be hidden in the noisiness that's behind the wavefronts, but you see the same idea. It's just a lot messier. All right, you still have the two parts that are moving left and right, but they're leaving a bunch of junk in their wake. And any sort of refined picture of what's going on, it's sort of hard to see. Okay, I got a bunch more, but they're going to get more exciting. Okay, Sim6. Sim6 is the same. It's the homogeneous problem, but now the thing that I've done here is I've spread the initial condition out over more lattice sites. Remember, I had squished a bunch near the origin together. Now I'm sort of doubling the wavelength of that initial condition. So now I'm squishing them together, but I'm squishing more of them together. So I'm increasing the wavelength, so to speak, of the initial data. And this one doesn't run quite as long as the first one I showed you like this, but it's the same basic phenomenon. There's a reason why I'm showing you all these things that look the same. One of the reasons is that it makes the letter W right now, and that's the letter that my last name starts with. And I find that to be very funny. But anyway, you see this stuff. But one thing you'll see here is that divot that I was mentioning before doesn't appear. It takes longer to appear. And that's attached to the wavelength in a way that I'm not going to tell that story. But it does happen. All right, so this is that. I got to do a couple more of these. So Sim7, there's 9 altogether. Sim7. All right, this is the same as the last one that doubled the wavelength. And now it's random. And you see it does the same thing. But one thing you might notice here, if you were carefully paying attention, is that it's still noisier, but it's not quite as noisy as the last one. The last time we did a random one. It's still noisy, but it's not as noisy. The noise is like little, I mean, it's still obviously there. It's not as clean as the homogeneous one, but it's a little less pronounced. This will just run to 75, I think. All right, Sim8. Sim8 is, I'm going to quadruple. I'm going to have a really wide initial condition. It's random, really wide initial condition. And it does this fuzzy thing, and it does exactly the same thing. It's a little bit slower. It seems to be evolving a little bit more slowly. Although if you tracked the sort of, if you plotted what the characteristic speed was, you would see it was basically the same as in the last one. The speed of the peak moving left to right. Okay. And again, it's not quite as noisy as you saw before. And there's the W. Gotta love it. So this will just run to 75, and then we'll move on to the next one. So, oh, this actually runs to 100. So the thing is there's a couple competing things going on here. One is there's the wavelength dynamic, but somehow the longer the wavelength is, the less noisy things look, the more clean the random problem looks. So what I'm going to do in this next simulation, this is the big ticket one, okay? I'm just going to let it run. It's going to do a lot of stuff, and I'm going to talk over it, okay? So what I'm doing in each one of these is, and each time it clicks over, I'm doubling the wavelength of the initial data, but I'm also zooming out. Okay, so each picture, I'm doubling the wavelength of the initial data, I'm spreading it out further, but to compensate just for that, what I'm doing is I'm including twice as many picture things on the screen. Okay, so I'm sort of scaling things in a certain way. I'm scaling the wavelength. But I'm also zooming out, and you'll notice that as this happens, it's obvious that when the wavelength is short and I'm not showing you many things, it's pretty discrete looking problem. I have a lot of X's, but as I increase the wavelength, it looks more like a continuous problem, right? Like this looks like a line the bottom curve looks like a graph of something over an x coordinate. So, and that's exactly what I want to capture, is that sort of if you change the wavelength of the problem and then correspondingly zoom the problem in the right way, what you should see is a wave equation. All right. This is a really, the problem we're studying here is really a homogenization problem, really classical homogenization. Let me at least start it again. We won't watch the whole thing, but just so we can capture this idea. You know, it looks pretty discrete, still pretty discrete. The wave equation there, it's pretty rough. Now it's starting to look a little bit more, you know, continuous, a little bit smoothed out, and then it's going to keep on going that way. So this is really a homogenization problem. As I increase the wavelength of the initial condition, the solution is sort of spread out over more and more of these random masses, and so some sort of averaging is going to be going on over those. Now this is random homogenization. It's involves, you know, a lot of machinery that I wasn't so familiar with before I started in on this project. But I'm going to tell you what the theorem is. I'm going to tell you, roughly speaking, how you prove it. And I'm probably not going to get all the way through that, but I think I can get to some of the key ideas. Now, so there it goes. And it looks pretty good. Okay. So let me cancel that. Let me stop the sharing. And I'm going to go back to the board. Okay. So I know it's morning there, but I'm drinking my dinner wine because I didn't think I was going to be doing this. So, but we're kind of on the same page. What's going to go on here? I'm going to sort of try to homogenize this problem. Okay. Now, one thing I didn't say at the beginning, but I should have said, is that this work is entirely joint with a student of mine, named PhD student of mine named Josh McGinnis. So let me tell you a little bit about the history of this project is that I had done some similar work on problems where the masses varied periodically, like there were 3 types of masses: mass 1, mass 2, mass 3, mass 1, mass 2, mass 3, mass 1, mass 2, 3. I had done that for a while, and I was interested in seeing what would happen if you change it to the random problem. And I had started this many years ago, and I got to a certain point and I got stuck. And the issue was that I didn't know any probability. And so I knew some of the homogenization theory that I'm going to talk about, and I knew how to make some predictions, but I didn't know how to close an argument. Josh, you know, was an advisor. It turned out that he knew some probability, and so I ran this past him. And he said, "Let's do it." And so all the sort of big picture is due to me, but all the nitty gritty stuff is due to Josh. So I was hoping he could attend this talk, but of course I screwed up the day. So he's great, and maybe someday he could come be a postdoc in Australia. I don't know, maybe. Just be awesome, but we'll see. So let me tell you, I need to write down the theorem correctly is a bit of a chore, and it requires a fair bit of you know, lingo and changes of variables. So let me give you the pitch here. So the first thing you got to do is you got to change your variables, and you got to do it in a smart way. So the first thing to do is you want to have a sort of, I don't know, generalized position coordinate, I guess you could call it. I'm going to have a new position coordinate. Instead of x, I'm going to have qj, and what it is this quantity, xj minus lj. I've sadly erased the board, but this was the thing. This is basically the force exerted by one of the springs, and this is the distance between the springs relative to the length, and I just multiply it by the spring constant. Okay, so this is going to be one of my new coordinates, and my other new coordinate is going to be v sub j, which is just the velocity of the jth mass. So this is my velocity coordinate now. Well, it's just literally velocity and q. So this is by using these as coordinates, I'm going to take my second order system, write it as a first order system. Okay. If you do that, you get this equation I'm going to call 2. And it has a nice symmetric form. It looks like this: Kj Vj plus 1 minus V sub j, and then Vj dot. Okay, this is really just this time differentiated. This is Newton's law, the second one. 1 upon mj, and this should be rj. And I wrote rj, but I really meant to write qj. Qj minus 1. Okay. So that's my new system. And of course, there's infinitely many of these guys. So this is really the same as the original system, but it's now written in these new coordinates. It's first order system, and you can see it's kind of symmetric, right? It doesn't look so different. The two equations don't look so different from one another. All right, so that's the system. I want to talk about the initial condition. Okay, what are my initial conditions going to be? So I'm going to take Qj of 0 to be phi of epsilon j, and I'm going to take Vj of 0 to be psi of epsilon j. So, and here 0 is less than epsilon is much less than 1. So epsilon is the wavelength, or 1 over epsilon is the wavelength. The smaller epsilon is, the more spread out the initial data is. Phi and psi are fixed functions. They're continuous functions. They're functions of a continuous variable. And what I'm doing is I'm sampling them at epsilon times the integers. That's another way to view this. Okay, so in the simulations I was showing you, psi was 0 and phi was a Gaussian. Okay, it was e to the minus x squared. All right. So you know, I'm just sampling these functions in some way. These functions are supposed to be nice. They're supposed to be like you know, continuous and of rapid decay at spatial infinity. All right, but that's fine. Okay. So what you do is you solve this equation with this initial data, and then the next thing you're going to do after you solve the equation. So now, so you've done that. You've done you've got your solution in hand. And I mean this sort of abstractly, of course. And then you need to coarse grain the solution, all right? Coarse grain the solution. Okay. So this language is from or at least I learned it from a paper by Milka, which does a problem similar to this, but where the coefficients are periodic. But let me explain what I mean by coarse graining. So I'm going to introduce a new thing here: Q epsilon capital X and tau. So this is going to be the coarse grained version of little q. Well, let me tell you what it is. Okay, I take q. Okay, there's q. This q right here. Now q is only defined in integers at j's. So I'm going to interpolate it to the whole real line. Okay, q is defined at j equals 1, j equals 2, j equals 3, j equals 4. But then I'm going to interpolate it, and there's a specific way that I'm going to interpolate it, but I'm not going to tell you what it is. Like you could just imagine that I connect it with line segments, and that would be fine. So I'm going to interpolate it. So I here is my interpolation operator. Okay. So I interpolates q. So now q. So this thing here is defined at all real numbers. All right. Just in a naive way, right? So like, you know, I've got. So this is, I don't know why I'm doing this so much, but 0 and 2, right? This is q of j, and then I fill it in with I q. Okay, that's all I'm doing. I'm just interpolating. So now this is a continuous function. Now the next thing I've got to do is I'm not going to evaluate this at I could just evaluate this at x, but what I'm going to actually do is I'm going to do it like that. So I'm kind of, if you kind of stare at this for a second, I'm kind of undoing what I did with the initial condition, right? So as epsilon goes to 0, phi, the initial condition for Q gets spread out, right? The bigger epsilon, the smaller epsilon is, the more spread out the initial data is. And I'm rather, more or less what I'm doing is I'm undoing that right here. So I interpolate it, and then I compress it back in, all right? And then it turns out I'm going to do the same thing, but in the time coordinate, okay? That may not be as obvious, but that's what you do, okay? So what you do is you spread out the initial data, solve the lattice differential equation, interpolate, squish stuff back in, and then you slow things down, all right? Or I guess speed things up. Okay, that's the idea. And then you have a similar thing for V epsilon. It's tau equals I V x over epsilon tau over epsilon. Okay, so this is a way from going from a discrete object that's spread out to continuous objects that are not spread out. Right. So then what happens, and this is the theorem. Let me write the theorem that Josh put the finishing touches on. Maybe, I don't know, in the fall. Okay, so here's the theorem. Let me write it down. So if the MJ and the KJ, well, they don't need to. So if the MJ are IID plus some conditions, those conditions are basically, they're positive, all right, that they're bounded strictly away from 0. So say you draw them uniformly from the interval 1 to 2, all right, something like that. So the MJ are IID with some conditions, and so are the KJ. Then for any t0 greater than 0. So this is going to be a sort of time horizon that we're interested in. This is how long we're interested in this this thing running. The following happens: the limit, as epsilon goes to 0 from above, of the supremum of t less than t. This should be tau. This is t0 of q epsilon dot tau minus q star. I'll tell you what q star is in a minute. Dot tau in the L2 norm equals 0. There's a similar expression for the v. I'm not going to write it down. There's a v star on it. So you pick your time, and you do your coarse graining, and then you send epsilon to 0. You get some object out at the end of the day. All right, there's something that this process results in. And this is almost surely. This is the big deal here. That's almost surely. Okay, it's not in expectation. It's not in distribution. It's almost surely. So this is really going to happen. All right. In the above. So I got to tell you what Q star is. Q star, and it's V star. Solve. Well, they solve a wave equation. They solve this wave equation. D tau Q star equals that number. I'll tell you what that number is in a minute. Dx V star tau V star 1 over m bar x Q star. So we call this one. Okay, let me write that down. What is m bar is the expected value of the MJs, and k with a thing on top of it is 1 over the expected value of 1 over kj. So this is a wave equation. This is a wave equation written in as a system. But if you wrote down what dt squared of q was, you would get dt squared q is k over m dx squared q. So this is really just the regular old wave equation. You can solve it using D'Albert's formula. You get a thing that moves left, a thing that moves right, and the wave speed is so that is the that's the theorem. So if you scale the initial condition this way, run the solution, interpolate, descale the solution, take the limit as epsilon goes to 0, you get something that solves a wave equation. All right. One last thing I should say is you might be wondering what the initial conditions are. Q star of x and 0, that's that function phi I was writing, and then v star of x and 0 is that function psi. Okay, they just go. You're picking the initial data for the wave equation from the initial conditions for the random FPU problem. If you think about it for a few minutes, is the way that you would do it. Okay, so is that okay? That's what the theorem says. How much time have I got? I know I started late and I was told 45 minutes, so I don't want to. I want to sort of try to make sure that I can get to something.
So formally speaking, I think you have about 10 minutes left, but I'm happy for you to finish your talk, and if people need to leave, then they can leave. But I think more people are more than willing to stay.
Okay, I'll just keep on going then. You can tell me to shut up. I'm okay with that. Okay. By the way, I have a little bow tie thing that I was going to wear. You know, I'm not even kidding. I was going to dress up. I was going to make a lot of like Ben Simmons jokes. You know, he plays for the Sixers. He's from Australia. I had all this stuff worked out. I was going to practice tomorrow. It's just not going to work. I have a T-shirt with him on it. Anyway, it's going to be great. Okay, so how do you prove this theorem? All right. So I'm gonna give you a whirlwind tour of it, of how the proof goes. But before I do that, I need to tell you what other people have done. And I'm just going to read this out loud. And if you're interested in getting the references, I'll tell it to you. There's been a lot of work on the constant problem where the masses and the spring constants are fixed. They're not variable at all spatially. In that case, if you include a nonlinearity, then you can go even further than what we've done here. And you can see that, roughly speaking, in this setting, you get something that's like a Kdv equation. You can get the wave equation thing, an analogous result that I've got written on the board in those cases, just sort of as a byproduct of what you get from the Kdv analysis. Of course, that Kdv stuff goes back to Kruskel and Zabusky, you know, and FPUT themselves. Back in the 70s, the rigorous results that I'm familiar with started in this sort of direction, started with Schneider and Wayne. Wayne was my advisor around the year 2000. For the linear problem with periodic coefficients, but in higher dimensional problems, that is where it's not just arranged on the line, but maybe it's on the integer lattice, or the integer square lattice, but with sort of periodic coefficients in that setting. Alexander Milken did a bunch of work around 06. In that work, the convergence that he gets is weak convergence in L2. It's not strong convergence. So our work is a little bit stronger in the sense that it's a strong convergence result. But we took a lot of the ideas from his paper. So there's a lot of stuff about the periodic problem in one dimension, some of which is by me and collaborators. Some of which is by Carolus Bruckner and collaborators. You get Kdv approximations there as well. That's also strong convergence results to Kdv-like equations. And Chris and I both worked on sort of parallel traveling wave work related to those problems, where you get sort of things that are like solitons, but they're not solitons. That's basically why I know Chris. Robbie introduced us because we did work on that same sort of problem. There's also a whole bunch of really high accuracy and interesting numerics about random wave equations, like random discrete wave equations like this. The oldest one I know is from the 90s by a fellow named Okada. Nestorenko did a bunch of work on this around 2000, and then some of Chris's collaborators, in particular Mason Porter and his other collaborators, did work on this much more recently. So there's a lot of different stuff about these sorts of problems. But as far as I know, this is the first sort of rigorous mathematical result on the random FPU problem. I'm happy to be wrong about that, but I've tried to find stuff and I couldn't. So so now let me get back to how do you prove this theorem. And I want to reiterate, Josh did all the hard stuff. So obviously I'm gonna have to leave out a lot of the details, but so here's the general idea. All right, you have your unknown qj of t. And so what I'm going to write it as is I'm going to write it as that homogenized solution. And like I said, a lot of the strategy here is sort of inspired by classical homogenization theory, Papa-Nicolau type stuff or whatever. There's this relationship between the real solution and the limiting coarse-grained solution. Now, when I wrote down the theorem, you'll notice I had done something where I'd interpolated Q, and then I had descaled the variables in some way. And I'm sort of just undoing that right here. I'm just going to write Qj, the real solution, as the limiting solution, scaled out in the right way, both in space and time. And then I need to put an error here. Okay. And then I have a similar expression for the velocities. Okay, so eta and Kc are my error functions, and I want to show that they're somehow controlled. All right, so what's my I thought about this hard. I thought about the best way to present this, and there's a victory condition. All right, so that interpolation stuff, the descaling, rescaling, limits, all that stuff. It's a bit of a there's a morass of details to work through there, but if you do it, you can get a victory condition. And so let me tell you what the victory condition is. The victory condition is that if the limit as epsilon goes to 0 from above of the supremum of t less than t0 over epsilon. So there was a tau in the previous theorem, but now it's t because the relation, this was called tau. And so if tau is less than t0, then t is less than t0 over epsilon. So this is a long time, because this is a very long time let's see, how do I do this? Eta of t, little L2, plus c of t, and little L2, times the square root of epsilon equals 0. Okay, so this is the victory condition. Okay, all this stuff here is a little hard. The limit is sensible. The soup over time, this is just telling you what time interval you're interested in. It's a very long time interval, right? It's 1 over epsilon. If epsilon's why you need to wait longer, which we saw in the simulations. The more spread out the initial data was, the longer it took for them to run. This is just the size of the error functions that are right here. And this square root of epsilon is there. What is that square root of epsilon all about? So I'm going to explain to you very quickly. Look, if you take a function, you spread it out, the norm gets bigger, right? I'm taking the same thing, I'm spreading it out over more and more sites. So the norm goes up. And so you got to sort of counteract that the fact that as epsilon is going to 0, the size of the initial condition is getting bigger, right? If I had it spread out over all the lattice sites, they'd all be separated by like 1 unit, and it would be really big. Okay, so the solution would be really big. So you got to countermand that. It's just a quick scaling argument. It turns out the right scaling argument is square root of epsilon. All right, so that's my victory condition. All right, I want that. If I can get this to happen, then the interpolation and the descaling, all that stuff, you can just. It's not necessarily easy, but you can grind it out. It's just that stuff. Okay. So that's the victory condition. You're not going to remember it, so I'm going to erase it. But just trust me, there's a victory condition. The great and much missed mathematician Walter Craig always said, if it moves, you differentiate it. So I'm going to tell you what I'm going to differentiate Eta and Kc, and I'm going to see what equations they solve. And I'm going to just tell it to you. So I'm just going to give you the Eta equation because the V equation looks, or the C equation looks much the same. You get something that looks like this. Plus Kj. Get V star here. Epsilon J plus epsilon. Epsilon T minus V star. Epsilon J, epsilon T. And then there's a minus epsilon K check. Dx V star evaluated at epsilon J, epsilon T. Now, what have I done here? I differentiated the equation that defined what Eta J was, and then I used the equations that V star, Q star, and Q and V solved, and I replaced a bunch of stuff. You do that, you get here, okay? So this is just an exact calculation. It'll take 5 minutes to do it. It's not so exciting. But you get this weird equation. Now here's the deal. I want to look at this blue term that's sitting right here. You'll notice that the way the shifts work out is that I'm evaluating V star at epsilon J plus epsilon here, and I'm evaluating it at epsilon J right here. So if I did a Taylor series expansion in this blue term, well, I'm doing the Taylor series expansion about epsilon J. Okay, so it's a little bit funny, but what I'm going to do is I'm going to expand this in epsilon around that as my base point. It's kind of a little bit funny, but what would I get? I would get V star of epsilon J as my leading term, and then the second term would be epsilon dx V star evaluated at the same point, and then I would keep on going. All right, so the point is that my blue term is equal to, well, it's equal to epsilon dx V star epsilon J epsilon T plus the next term will be epsilon squared over 2 dx squared V star at that same point, plus so on and so forth. So what I could do is, okay, let me just call this epsilon squared J, okay, all that stuff. It's just junk, it's very small. And then I replace this in the above, and I get Eta J dot equals Kj Cj plus 1 minus Cj plus, okay, then you'll note that this looks a lot like this, but they come with negative signs, and this is the average thing, and that's the Kj. So you get Kj minus K check times dxv star epsilon J epsilon T plus epsilon squared J J. Okay, so that's what you get, and there should be an epsilon right here. All right, now, so I want to tell you what goes wrong, and then I'll try to very quickly tell you what goes right. Okay. So you get a very similar equation to this for C, and then this whole problem arises from a mechanics problem, and that mechanical problem is conservative, has conserved energy. And if you stare at that conserved energy and see what it means for this thing right here, you learn a lesson. You learn a lesson, and that lesson, after some work, is that the conservation of energy tells you that if you measure the norm of eta in little L2, that it's less than or equal to a constant that depends on the k's and the m's, but it doesn't really matter that much, times epsilon times the supremum of dxv epsilon dot epsilon T, and this is in little L2, and then plus smaller. And this is times T. Okay. Now things are important. Okay. Now there's some stuff that's going to happen right here. Okay, that constant I don't care about. This is the supremum over T less than or equal to. Yeah, this is the supremum over. It should be an S less than t, and that should be an s. Okay, so that goes in there. All right. Now the V star is solving a wave equation, and so really this doesn't depend on time in an interesting way. It's just it's just propagating wave or whatever. But there's an issue here, which is I'm measuring this. I'm taking my function, I'm sampling it at epsilon times the integers, and then I'm computing the L2 norm. If you figure out what that is, this is epsilon to the minus 1/2 times, there's a constant here, of course, times V star in L2. Okay, so there's a loss that goes on here. All right, that loss is a problem, but there's that victory condition that I told you about that had an extra square root of epsilon in it. So what? Okay, so maybe they'll cancel out. But now here's the deal: the victory condition. So the point here is that this is less than c epsilon to the 1/2 times t. Okay, that's what this is. But then I need this. Okay. I need to supremize this over the interval 0 to 1 over epsilon. So if I put the sup over t less than t0 over epsilon here of this quantity, multiplied by the square root of epsilon, I get that this is less than or equal to a constant. I needed this to go to 0 in my victory condition, and I don't get there. Okay, I don't get there. Now, the reason that I don't get there is because of that term that had the kj minus k hat on it. All right. Ugh. All right. So that's a bummer. My victory condition doesn't work. And if the thing was constant, it would have worked. By the way, if the kj was equal to its average, then that term would be there, and this actually would have worked fine. So what are you going to do? All right. So you'll notice I barely said anything about the randomness here. So let me tell you how you fix it, and then we'll go on. So let me remind you of what the equation was. Eta j dot was kj cj plus 1 minus cj. Plus epsilon, not epsilon squared, epsilon kj minus k with a hat on it, dx v star, epsilon j, epsilon t, plus small. Okay, so that's the equation I'm looking to solve with my victory condition, and this is the origin of a lot of problems. If that was epsilon squared there, I would win. All right, but it's not. It's epsilon. So what you do is you make a new change of variables. You're going to let eta j and cj. You're going to let them be a new error function, cj. Okay, plus something small. I'm going to try to adjust them. And if I put just the right thing here, maybe I can kill this term off. And then everything that's left will be small. I don't need to worry about it. Okay, it's classic math, applied math sort of trick. And I know what that thing is. There's a procedure by which you can figure out what it is, but I'm going to tell you what it is, at least roughly. So here's the idea. It's going to be something that looks like this. Of course, this is all evaluated at the right point. And then, this is kind of an ansatz that I'm giving you right now. But that's what it's going to be. So let me tell you what's going on here. One of the key problems is that dx v star right there. This thing is dx v star times something pure, something random, right? That's what it is. So basically, I'm going to adjust my guesses to look kind of like it. Chi j and gamma j, they are sequences. I don't know what they are right at this moment, but I'm going to tell you what they are in a second. I'm going to leave them undetermined. And then if I can figure out what they are, maybe this term will die and everything will work. Okay, so you plug that in, and then you get that eta j tilde dot. Everything looks a lot alike, but then it changes a little bit. C tilde j plus 1 minus C tilde j plus epsilon times kj times times plus 1 minus gamma j plus kj minus k check times dx v star plus OK. Right? So if you plug that in and you grind everything out, this is what you get. So my term, which is bad, is now this term. Okay, that's the one I want to kill. And this tells me exactly how to select gamma j. I just make this thing in the blue box, I make it equal to 0. If I make the thing in the blue box equal to 0, if I make the thing in the blue box equal to 0, then I get the following thing. I get gamma j plus 1 is gamma j plus 1 minus, I guess it's actually, it's kj, it's k check over kj minus 1. Okay. That's what it is. That's what the gamma is. And now we're into probability, because that's a random walk. Gamma is a random walk where the step size is k check over kj minus 1. And because of the way I picked that, what k check was to be the harmonic average, that driving piece right here is mean 0. So that's a classic random walk. Gamma is a classic random walk in the time variable j, the spatial index variable. Okay. So now you can start bringing to bear some information about random walks. Now, at first I was quite excited about this, but then I realized something. I don't know much about probability or random walks, but the one thing I do know is that the expected value of the size of the random walk squared is equal to, roughly speaking, the square root of j. Okay, I think I said that slightly wrong, but the point here is there's this famous result about random walks that says that the expected value of gamma j squared is like j. It's like the absolute value of j. Okay, so it's the central limit theorem, really. Okay, which is to say that this makes you think that gamma j, if you're just being very naive, as if, say, you were a guy who spent their whole life doing nonlinear waves and had never really thought too hard about, probability before, you might think, oh, that just really means that I can just think of gamma j as being like the square root of j, which is not true, but that's what I had thought. Okay, so if you do that, if you believe that gamma j is like the square root of j, let me draw a picture for you. Somewhere in my problem, I had gamma j times dx v star epsilon j, epsilon t. That was the object that I had in my problem. So let me draw this now. Okay. Here's the j-axis. Now, what is this? Okay, that's a spread out thing that's propagating with speed c. So let me draw it like this. It's spread out. Its characteristic wavelength is like 1 over epsilon. It's moving to the right. That's the blue part. Okay. What is this thing? Well, in my naive version of things, it's the square root. Okay. So you can see what happens here. As this thing moves to the right, it's moving into the zone where the green thing is big. All right. And how long do I need to run this for? I need to run this up to t equals 1 over epsilon. The speed of the wave is roughly speaking 1. And so I need to get all the way out here to 1 over epsilon, where this is like 1 over the square root of epsilon. And I was counting on something being small in epsilon. I'm getting back an extra square root of epsilon from this sort of ham-fisted probabilistic argument. Now it turns out that if you squeak by in the victory condition, if you follow all this through, that square root there, that square root j that you're picking up that's causing some things to grow, allows you just to squeak by, and you can prove the theorem. But then what Josh told me when I told him, when we were talking about this, like, that thing that you're saying about the expected value, it's not true. It's the random walks are more complicated. That's a result about expectation. That doesn't mean that there's a bound on it, right? It's not that simple. I was quite disappointed by this, but he's a smart kid, so I was, I believed him, and he was right. And I taught a probability class so that I could understand what he had told me, and it turns out he was totally right. So, but then he went digging, and he learned about this thing called the law of the iterated logarithm. All right. So maybe you guys know about that. I'd never heard about it before, but it's a really powerful theorem, and it's it's relatively old at this point. But it's an almost sure statement about the growth of random walks. And let me tell you what the law of the iterated logarithm says. It's real cool. It says that if you have a random walk, the lim sup of the random walk, if you take your random walk, which I'm going to just call gamma j, and you divide it by the square root of 2j ln of j, that's the iterated logarithm right there, is equal to sigma. And this is the standard deviation of the random variable that's driving the whole thing. Okay. And this is true almost surely. Another way of saying this is that gamma j exceeds the graph 2j log j only finitely many times. Okay, it can go over it finitely many times. It could go over it 5 billion times, but it doesn't go over 5 billion times. All right. So from this, you can back out that gamma j is less than or equal to some constant that's realization dependent. Okay, depends on the choices of the m's and the j's times this thing, 2 ln j. Okay. And now this is almost what I had before. Remember, my dream was that this was the square root of j, and now I've got this double logarithm right there. And it turns out that, like I told you, you just kind of squeak by if it's one square root of j, but there's just enough wiggle room in there to get you to go by with the extra logarithms in there too. And then, okay, I've kept you too long, and whatever. So I apologize for that, but that's the end of the story. With the law of the iterated logarithm, you can get in there and you can figure it. You can push everything over the goal line. And that's the story. So thank you for your attention. Again, I'm really sorry that I screwed up the day. I'm quite embarrassed.
No, that's perfectly fine. Thank you, Doug, for a very interesting talk. And again, for accommodating the time zone. I probably should have been more clear also on the day. If anyone has questions for Doug, please feel free to unmute yourself.
Hey, Doug, thanks very much for talking. I enjoyed that a lot. I do have a question.
Sure.
As you know, if you do something with some different powers, instead of going to a wave equation, you would expect it to go to Kdv. You mentioned that.
Sure.
Do any of the steps, is there a point at which the nonlinearity causes problems for your argument if you were to try a Kdv tending equation instead?
Okay, so I'm going to tell you that this is, of course, what I wanted to do. I wanted to do Kdv approximation.
I figured that was
But
probably.
here's the deal. You can't possibly get there. All right, so the Kdv approximation is on a longer time scale. So here, this time scale is 1 over epsilon. And then the Kdv time scale is 1 over epsilon cubed. So basically the way a Kdv approximation works is, okay, you put the nonlinearity in, you scale the wavelength just like I did. You also scale the amplitude. You make the amplitude small in a way that's linked to the scaling of the wavelength. To leading order, you get the wave equation again. You factor out the wave equation dynamics. That is to say, you put things into a moving reference frame with the right speed. And then the emergent dynamics from there are Kdv. You need, how I said you just squeak by here, getting the estimate to work. You need a lot that what happens in the homogeneous problem or the periodic problem, if you open that up, that extra room that you get, not just squeaking by in the victory condition, allows you access to the longer timescale dynamics. Okay, you don't have that here. And in fact, and this is the thing that's really cool, is that if you run the simulations and you put the nonlinearity in and you do all this stuff, it just doesn't work. It's just not true. There is not a Kdv dynamic in the random problem at all. What happens here, that ugly junk that was in between the moving things, when I did all the simulations, how there was all that noise in between, that comes at the cost of the amplitude of the solution, right? Because it's a conservative problem. If something's moving, something somewhere else is not moving. And so if you run these simulations, what you'll see is that the attenuation and the amplitude of the problem over very long time scales, with or without nonlinearity, is quite fast because it's just leaving this like ugly detritus in its wake. Now that detritus is relatively small in amplitude, but it's spread over many lattice sites, and so it just eats up all the energy in the problem. So there is, to me, no chance of getting Kdv-like approximation. But I think there's something else. I think there might be. I'm not sure. I'm really going out on a limb here. I think there might be something like a heat equation type approximation, which incorporates some of this extra loss of energy. I think that the next order correction is not conservative.
What's your initial?
Overall problem is, but the approximating equations are not. But I don't know how to do it. I told Josh he had to do it. He's like, I don't know how to do it. So.
I mean, it'd be interesting if you could rack on some extra conditions on the randomness, because obviously it strikes me that, you know, if rather than a finite range, you just kept it to within a very narrow range, then maybe you could limit the variability of your parameters to a point that, and that would be super interesting, right? Because then you could expand that and see how KdV could transition to your heat style equation.
Well, also,
so you can actually link those.
Doug, what's your initial condition that you're starting with, Doug?
So in these ones, it was always just e to the minus epsilon n squared.
So when you try to do the KdV one, what happens if you start with like a Sech profile, something that's actually a soliton in the KdV wave? Right?
All right, so it doesn't. It
still doesn't work.
So what you see in all these problems is the initial dynamic is the wave equation. The initial condition, whatever it is, Sech squared, e to the minus x squared, whatever you want it to be, splits into two parts that move left and right. Now remember, in the lattice problem, it takes a long time to see, like a solitary wave just moves, right? So that's not any different than general solution of the wave equation, right? Wave equation just also propagates; doesn't care what the profile is. But if you do it, and you have to ask yourself, which Sech squared am I going to do? Like, is it going to be 2 Sech squared? Is it going to be 3/2 Sech squared? X over 2? You don't know, right? Like all these coefficients are in there. You try to do that, and you just don't get anywhere. The randomness on timescales longer than 1 over epsilon eats everything. Completely eats everything. I have this figure that I was going to include, but I didn't have time because I thought it was Wednesday. I mean, I thought it was Thursday. Yeah, whatever. I feel really bad. Where you just compare the amplitude degradation in the linear problems versus constant, periodic, and random. And there's a small attenuation in the amplitude in all three problems. It's a dispersive problem, and you expect there to be an L infinity decay for dispersive problems. For FPU at constant coefficient, it's like t to the minus 1/3. But if you just graph the attenuation, it's like it's marked. It almost looks like it's exponential. It's not. But it's so much faster in the random problem that it takes a while to kick in, depending on the wavelength of the initial data. But it takes forever. But it's faster. So
I have another question for you about, which is these are fixed distance masses apart, right? You're just like you've set at them at 1 or something, right?
Yeah. Well, I mean, remember I had that LJ in there. Yeah. So they're actually you can play games with that if you want.
Yeah.
But yes, basically speaking, I've got it set up so that they're all fixed distance apart. But if you wanted them to be of a different spatial thing, then you could sort of change coordinates so that they were.
But they're not random as well, or?
Excuse me?
Are they randomly distributed in space as well, or no?
No, they weren't. Not in the ones I showed you. Yeah. The distance between them, like I said, it's that's not really a degree of freedom you have in selecting things as it happens, just by changes of variables.
Well, I was going to say, then it just seems like your initial wavelength, it'll be like the ratio of the initial wavelength to the distance that these things are that will determine.
You can work that out, yeah. That's a different limit you could take. But it really boils down to the same. Yeah. There's only so many things you can really play with in the problem. And if you want to turn that knob, you can do, but then you lose some flexibility on other things.
Sure. Yeah, I have one more like maybe dumb question, which is in the beginning you showed this the homogeneous problem. This is probably my ignorance. You showed this homogeneous problem, but you also showed that it had dispersion, like nonlinear, like dispersion in it. But the linear homogeneous problem has dispersion, like the
Absolutely, yeah,
it does.
absolutely, yeah. It's
So okay, but,
that's actually relatively easy to work out. I mean, I'm not saying that you should know this. I'm just saying that if you want to know why, you basically apply a Fourier transform to the problem. Now it's a discrete problem, so you might be wondering like, what's the Fourier transform of the sequence? But there is one. It's just the inverse. It's what you do to sum a. If I give you a sequence and you multiply it by complex exponentials and sum it, that's a Fourier series. So it's basically you take the Fourier series with coefficients that are the unknowns. Then you diagonalize the problem on the Fourier side as you would expect, and you see that it's got a dispersion relation,
as a bonus,
and the dispersion relation is frequency dependent. It's dispersive. Yeah.
I mean, on some level, every discrete equation of that form is going to be a little bit dispersive, just because it's a term down in the Taylor series, and you're always modeling it as a continuous Taylor series thing. So you naturally expect
that's absolutely correct.
Yeah. Everywhere.
Non-local problems that are conservative. This is, I mean, you could view it as a non-local problem because it has to see to the left and the right by a fixed distance, not just a derivative. You know, they tend to be, for the same reason that Chris just said, dispersive.
Yeah, unless they're like really carefully tuned otherwise.
Yeah, it's but FPU is the classic. I mean, FPU is the classic dispersive lattice differential equation, right? It holds that like a role in the lattice differential equations community that Kdv does or NLS does for you know, scalar ODEs or PDEs. Sorry.
Okay. Are there any more questions? No. If not, thanks again very much, Doug, for doing this on such short notice.
No problem. I wouldn't mind talking to Chris and Robbie just for a couple more minutes.
Yeah, I'll hang
you guys
around.
can hang out.
yeah, for sure.
I'll stop the recording, but I'll leave the meeting open if that works for you.
That'd be terrific. That'd be terrific.
Okay. All right. Thanks, Doug. Take care.